of lectures by Rafael Alves-Batista, an expert in cosmic ray particle propagation, and he's going to give 4 lectures. So this is the core of our school. It's very important for everything that we are seeing, because we are going to see the theory behind and some of the phenomenology behind the particles that produces the gamma rays or the neutrino signals that are being discussed in the other lectures. So Rafael is a professor at the Sorbonne Université, and he's Brazilian. He's worked in Brazil for many years, and it's really a pleasure to have you here, Rafael, and I hope you enjoy his lecture.
Yeah.
Thank you very much.
So thank you very much, and thanks for the invitation to give this course. Today, especially this morning, I'm going to start slow so that you can wake up. Yeah, and let's get moving. So I think this course is actually very important, as Ulysses said, because whether you are doing neutrinos, yeah? Yeah, where do I switch them off? There's probably something here, okay. Better? Yep. Okay, this color is weird, okay. It was not supposed to be that green, I think. Yeah, so to get started, I'd like to motivate this with this plot. I'm sure you've seen this many times in your life before. This is essentially the spectrum of cosmic rays. You see here the energy. The first thing that it's remarkable for everybody, at least to me, is that, well, it spans several orders of magnitude, almost 11 orders of magnitude in energy, which is quite a lot. And if you look at it, it's roughly, well, very roughly speaking, a power law with some breaks in other places, but yeah, it covers many orders of magnitude in energy, and that's rather remarkable. And what we are going to do here, we are going to study high and ultra-high energy cosmic rays. So there is no good definition for that, okay? So I'm not really separating the definitions here of what is an ultra-high energy cosmic ray and what's just a high energy cosmic ray or very high energy, I don't know. I'm going to mix these definitions, okay? But it doesn't really matter. So when I'm talking about these high energy cosmic rays, I'm usually referring to those above 1 PV. But what we also see in this plot are high-energy neutrinos here. These are high-energy neutrino measurements by the IceCube Neutrino Observatory in Antarctica. And here, for example, we see this gamma IGRB, isotropic gamma ray background. So these are high-energy gamma rays. And this picture, it's very interesting to motivate everything that we're going to talk about. And I suppose since this is an astroparticle school, what most of us work with, I think this is kind of unavoidable. Because whether you are doing gamma rays or neutrinos, you are ultimately, if you're thinking in terms of astrophysics, you are doing also cosmic rays, right? In some sense. So everything that we're going to learn here are skills that are going to complement what you're doing, even if you're doing gamma ray observations on CTA, for example, or other experiments, or neutrinos, and so on. I'm going to focus mostly on this, but at some point I'm going to mention also the other messengers as well, because they do provide complementary information, and that's essential, especially within the multi-messenger approach. Nowadays, right, we need to think about all these messengers together. And one thing that is very interesting here is that, well, just look here at this 10 to the 9 GeV, so 10 to the 18 electron volts. Suppose I draw a horizontal line here. It's rather remarkable that the E squared times the intensity, right, for all these different messengers, they are comparable. This might be a coincidence, this might not be a coincidence. Whether it is something physical, it's worth investigating and try to answer that. So there might be a connection, actually, between these high-energy cosmic rays in this energy range, these neutrinos in this energy range, and these gamma rays. We are going to see that, I think, tomorrow, or maybe on Friday. I haven't decided on the order yet. It depends how far I can get to today. But there might be a connection between all these messengers, right? And the source of this connection would be the high-energy cosmic rays that we are going to study today. So in today's lecture, actually this morning, the first one in the morning, I'm going to start very, very slow so that you can wake up. Just telling the history, because I'm pretty sure that you've heard that before, but you need some time to wake up. And then I'm going to talk quite a lot about air showers and cosmic ray observatories, because this is the detection principle. This is how we see the cosmic rays and how we reconstruct their properties, their energy, and so on. Everything that we use to do the final product or the science, in the end, we need to understand how to reconstruct the cosmic ray showers. And then I'm going to talk a little bit about how to interpret the measurements, the relevant observables, that we usually see. For example, we've just seen something that we call spectrum, or it was written intensity, but it's also called flux, and there are small distinctions in the definition, but the name doesn't really matter as long as you understand exactly what you're doing there. And then finally, I'm going to present a brief overview of some recent measurements that we've had in cosmic rays, in high-energy cosmic rays, and ultra-high-energy cosmic rays in particular, so that we can kick off the other lectures. And I'm going to use this particularly to motivate the theory that is coming later, okay? So let's get started. A very brief historical overview, or maybe not that brief. So I'm going back a few hundred years, so it's not that brief. The first observations of cosmic radiation was actually, they date back to the 18th century. Coulomb, from the unit Coulomb, he noticed that electroscope would discharge spontaneously, and with that he inferred that there was something in air, right? He was using some type of electroscope. This is from his publication at the time. And with that he inferred that the air was actually conductive, so it was allowing the propagation of charged particles in some sense. And then later on, 1 century later, there was Crookes from Crookes tube, and he showed that if you do the same type of analysis with a lower air pressure, the effect becomes weaker. So there was something apparently in the air, if this result is true. And then in the late 1900s, there was the discovery of radioactivity. So that was a natural source of ionizing radiation. The discovery of radioactivity, as many of you probably know, I think it was 1896, Henri Becquerel. He actually, this is one of his observations. He had something in his drawer, and he had a radioactive source there, and he just put this emulsion, so this is a photographic plate, underneath, and then he got something, and then he started speculating and tried to understand why would he get, why would his photographic plate change, and then he inferred that there was something with that material that he was studying at the time. And why am I going back so much here? Well, that's because we need to understand the context in the late 19th century to understand the discovery of cosmic rays and actually the trajectory that it took afterwards. So people here, in 1900, more or less, they were very interested in radioactivity. There was Marie Curie, for example, discovering other radioactive elements. And people were thinking, okay, we have these radioactive elements, so there is something, you know, there are natural materials that emit radiation. And people, if you connect with that, with the natural discharge, spontaneous discharge of air, well, you could argue in principle that there is something in the materials on Earth, like there is rocks. Rocks could be radioactive, and some of them actually are. We mine them, usually. So these two people, Hans Geitel and Julius Elster, they confirmed the existence of this atmospheric ionizing radiation from before, but nobody actually knew the origin of that. And considering the context, I mean, if you are in 1900s, someone tells you that there is atmospheric ionizing radiation, and then 5 years before that, someone discovered radioactive materials, of course, the logical conclusion would be, there is something on Earth, like the rocks, maybe, radioactive material. So people started speculating about these two hypotheses, whether it was terrestrial or extraterrestrial. So just let's compare them. In 1901, Wilson, he went underground and he showed that the ionization level did not decrease. And then there was, a few years later, someone just flew to the Atlantic, and this person, Eve, he saw that the level of radiation in the Atlantic was not more or less the same as in the continent. Therefore, this is a very strong indication that if the hypothesis that the source of the ionizing radiation in air was true, this would favor the hypothesis of a cosmic extraterrestrial origin, because had the terrestrial hypothesis been true, he would have seen a decrease in the amount of ionizing radiation as he went to the ocean. And then a few years later, the same people from before, Elster and Geitel, they went down a mine, and they saw that the ionizing radiation decreased. And at this time, actually, the result was a bit unreliable. And this actually strengthened the hypothesis of a terrestrial origin, so this was contradicting the previous result. But later on, in 1909, Theodor Wolff, he went up the Eiffel Tower. So the story says that he was on holidays with his family, and for some reason, he just decided to take an electroscope during holidays with his family and go up the tower to do some measurements, right? This is a very physicist thing to do. You go on holidays, and then you take your electroscope. So he went up, and then he found a mild decrease compared to the ground level. This was inconclusive, but it was kind of favoring the hypothesis of a terrestrial origin. Later on, I found out, actually very recently, that the material that composed the tower, the Eiffel Tower itself, was interfering with the measurement. So this is a very iconic case of systematic uncertainty that was not accounted for. And then in 1911, I think this is what I personally consider the first convincing evidence of cosmic rays extraterrestrial origin. Domenico Pacini, he goes down the sea, and he found a 4.3 sigma result, showing the reduction in the ionization level. And this is a very strong result, and at the time, I think this is more or less when the opinions of the decision, when the community actually decided that this hypothesis was stronger than this. So moving on, in 1912, and I think this is where most cosmic ray lectures start, they show this plot, like Victor Hess flying his balloon, and showing that the ionization level, the dependence of the ionization level, so showing that it increases with the altitude. I think this is what most people consider the birth of cosmic ray physics, but there is a lot of background information there, which is important. And then in 1913, Kohlhorster, he went up even higher than Hess, up to here, maybe up to 6 kilometers with balloons, and he confirmed Hess results. And then the term cosmic rays was not coined until 1926 by Millikan. And then in 1932, there was all those particles being discovered, like the positron, and these all came from cosmic rays. So they had cosmic ray observations, they had many of them photographic emulsion plates, and they were looking for new particles in these emulsion plates. This I find a very interesting piece of history, because this is the New York Times. And in the New York Times, they had something like Millikan retorts hotly to Compton in cosmic ray clash. Imagine nowadays you hear about cosmic rays in the New York Times, right? That would be good news, I think, considering everything that's going on. Yeah, but what was going on here is that even though they had kind of confirmed that there was ionizing radiation coming from outside, they did not know what it was. And now we are here, 100 years later. We have a much better idea, but we still don't know the exact chemical composition of the cosmic rays at the highest energy. So, it's been 100 years, and we still don't have the real final answer. Yeah, but I put this here because Millikan was supporting the hypothesis that cosmic rays were actually like gamma rays. And that's why I mentioned also that historical context, because in the turn of the 20th century, there was the discovery of radioactivity, but also X-rays. And Millikan thought that cosmic rays were like X-rays, like electromagnetic radiation of very, very high energy. Okay, moving on, there were several experiments in the 30s by, for example, Alvarez and Compton, and separately by Bruno Rossi, and they noted that the cosmic rays are mostly positively charged particles in the atmosphere, and this is actually the first hint that there is something going on. Why would they be mostly positively charged? This is the first hint of what would later become like what we do today, kind of cosmic ray physics and the air shower physics. And in 1936, there is the Nobel Prize to Victor Hess and Carl Anderson for the discovery of cosmic radiation and for his discovery of the positron using emulsion plates. And in 1938, it was actually when Pierre Roget, which names the observatory that I know some of you here work on, and Roland Mays, they discovered the extensive air showers. This is actually just a snippet of their paper at the time. And here already they were discussing the origins of these cosmic rays because they observed extensive air showers, which we are going to talk about now, and they inferred cosmic ray energies beyond 1 PeV, so 10 to the 15 electron volts. And at the time, this was not really something that was known. And they were surprised, and they were actually, I think, as far as I can tell, one of the first people to start speculate systematically in many publications about the origins of what today I'm going to call high-energy cosmic rays. And then between the 1930s and 1960s, there was the golden age, what I call the golden age of the cosmic ray physics, which is when particle physics was essentially cosmic ray physics. They were the same thing. The positron, the muon, the pion, the kaon, and so on. Many particles were discovered with cosmic rays. For instance, here you have, this is from Cesar Latte's original paper of the discovery of the pion. You can see the collection of photographic plates here, which they used to infer how the pion was discovered. Right, so what we saw now with this very brief history is that, well, in the beginning there was something in the air, and this is not a name of a movie, of a bad movie, something in the air, which is actually does exist and it's terrible, but there was ionizing radiation. The radiation is extraterrestrial, that we know, and then there was the birth of a new field, which is what we call today cosmic ray physics. And then between the 40s and the 60s, people started, with the idea of extensive air showers, people started deploying instruments over larger and larger areas. And in 1962, you can see here, I think this is, if I'm not mistaken, this is John Linsley. There was this experiment called Volcano Wrench. This is a wrench. And he deployed a bunch of water Cherenkov detectors. Here he's poking a snake, apparently, according to the tail. I don't know if that's true. But yeah, in 1962, in these experiments, they discovered the most energetic particle until that time, which was a cosmic ray with more than 10 to the 20 electron volts. And from 1938, there were like the discovery of air showers, 10 to the 15 electron volts. And now we are talking about 30 years later, less than 30 years later, about 10 to the 20 electron volts. 5 orders of magnitude in energy. That's quite a lot. Okay, so knowing this history, now what are cosmic rays? Well, most of you already know the answer. I'm going to define then just what a high-energy cosmic ray is, and just for the sake of this lecture, this is my definition. This is particles with more than 1 PeV, and I'm going to define ultra-high-energy cosmic rays. Oh, this is completely wrong. I meant 1 eV, not 100 eV. Okay, that's my definition, so 10 to the 18 electron volts. And but the question is, why are we interested in high-energy cosmic rays? Well, the LHC does particle physics up to 10 PeV, more or less. And the energy of ultra-high-energy cosmic rays with 10 to the 20 electron volts, they are comparable to a football. If you kick a football, a penalty kick, that's more or less the same energy that you get in a single particle. We are talking about like a proton or an atomic nucleus with the energy of a football. That's quite a lot. That's rather remarkable. And now, back to this plot. we see here many types of particles, but let's focus on this upper part here, which are what I'm generally calling the cosmic rays, including all types of particles. So the low energy ones, they tend to come from the sun. They are responsible, for example, for the northern lights. And here we have this band, which corresponds to galactic cosmic rays. Galactic cosmic rays can have very low energies up to very high energies. We actually don't know where this ends, and this is one of the open problems in the field nowadays. We don't know when at which energy the galactic cosmic ray spectrum ends, and that's something that we would like to answer. And we also don't know where the extragalactic cosmic ray spectrum starts. So we observe all that. We would like to separate each component individually, but we cannot, which is why many of us have jobs nowadays. So there is this region here where the green and the orange are overlapping. This is what many people call the transition region. I wouldn't call this definitely the transition region, but this is what we think is the transition region. Something between maybe 10 PeV and 1 eV or so, where the galactic astrophysical objects could produce cosmic rays, maybe up to here. Although this is kind of difficult from the theory point of view, to have galactic sources up to 10 to the 18 electron volts, but not impossible. This extragalactic component, we don't know how low in energy they can go. We need some kind of, maybe it can dominate over the galactic one, maybe it cannot. We know that this part here, it's galactic, the green part, up to 1 PeV more or less. We don't know what happens afterwards. And how do we detect these particles? So if you look, let me go back actually. Look at these diagonal lines here. So if we want to study these particles and detect them, we need, to have instruments covering a very large area depending on how many of these particles we want and depending on the energy. Here, for example, we get 1 particle per square meter per year, more or less in this region. Here we get 1 particle per square kilometer per year. And here, per century, right? So if you get only 1 particle per square kilometer per century, that's not a lot at all. You would need to wait 100 years to get 1 particle on average, right? Well, but you could tell me that you can have then 100 square kilometers and then do that in a year. Sure, for 1 particle, still not good. You want to do statistics. You want hundreds or thousands of particles, ideally. So that's why we need to have very large instruments covering very large areas, like many of the detectors that we know exist, like the Pierre-Roger Observatory, for example. We have at slightly lower energies LASSO. You're going to hear today about SWGO, which cover areas that are quite large, depending on the area, the region of the spectrum that they are interested in doing science. Okay, about air showers. So what's an air shower? An air shower, it's when a particle comes from outside, it arrives at Earth, it impinges, it hits the air at the top of the atmosphere, causing a cascade of particles. So what we are seeing here, it's actually, this is a view of the city of Chicago where this animation was made. And what we are looking at the top, there is a particle coming in, it's hitting, interacting with the air, producing hundreds, thousands, millions, billions, trillions of other particles depending on the energy. And those secondary particles are the ones that we actually get here at Earth, at ground level. So with a sample of these many, many particles that arrive at our detector, we have a very difficult job. Well, nowadays it's much easier because people have been doing that for 100 years. But before, in the beginning, I imagine this was very difficult to do. We need to get individual particles, and then we need, which is just a sample of all the particles, and we need to reconstruct the properties of the particle that came up there. And when I say reconstruct the properties, we want to know the energy. Well, the energy is usually proportional to the number of particles here and the profile and so on. We want to know the direction and this type of thing. So that's what reconstruction means, and that's a very important part of the job of a cosmic ray physicist. Everybody who works in a cosmic ray collaboration, and also in gamma ray collaborations, or whatever collaboration, whatever instrument detects air showers, reconstruction, it's an integral part of that. There are many types of observatories and detectors. Just to illustrate a few of the detection principles that we have. Well, let's imagine here it's the atmosphere. Let's imagine that we have a cosmic ray hitting the atmosphere. Once again, it produces showers, many, many particles. Of course, this is simplified. The first few interactions at the top of the atmosphere excite the nitrogen in the air. And this process of excitation, the excitation emits fluorescence light. So we can just have something like a telescope observing this fluorescence light at the top of the atmosphere from these first few interactions. We can also do the same from space. We can just have a satellite looking down with a telescope looking down into the atmosphere, looking at this fluorescence light. We currently don't have any big instruments. We just have prototypes in this direction. But people are thinking about that nowadays. Where am I? OK. Yeah. So these showers, they keep developing. There are two components here that we can see. There is this one in red and blue. It's what we call the electromagnetic component of the shower. We also have the hadronic component of the shower here, which are the other particles, the hadronic ones. And then we get, what we usually get here at the end, we get a lot of muons at detectors. So we have these things here, particle detectors. They are, for example, water Cherenkov tanks. They can be scintillators, just a plate that scintillates when one of the secondary particles cross them. And these interactions, they also produce, especially the electromagnetic component, it leads to the production of radio emission, so in radio frequencies that we can detect using antennas, radio antennas. If we had a gamma ray, well, the detection principle for gamma rays, it's the same. We have a particle shower. You can barely see it here, but there is this blob. This is a particle shower, and in the end, it leads to the production of atmospheric Cherenkov light, and we have Cherenkov telescopes here detecting these particles. This is the working principle of observatories like HECRs in Namibia, for example. We have MAGIC in the Canary Islands. We have Veritas in the USA. For example, this is what we call imaging atmospheric Cherenkov telescopes. We can also have, well, gamma ray detectors in space, but it's slightly harder because, well, for many reasons. So we are kind of limited in energy by technical reasons to do that in space. The Fermi satellite, for example. The Fermi satellite can only operate up to 300 GeV. It's one of these gamma ray detectors in space. OK, and now I think most people are already here, and we all woke up, I hope. So what we can start doing is we can start going for to understand the shower physics a bit better. And I'm going to use a toy model for that, something called the Heitler model from 1944. So this is kind of a 100-year-old model, 80-year-old model. So in this Heitler model, what we have is the following. We have a primary particle interacting in the atmosphere. I have to say that this Heitler toy model, it deals with electromagnetic showers only, so electrons and photons. And it simplifies a lot the development of the shower in the atmosphere, but it does capture, as a good toy model, the main features of this process of air shower in the atmosphere. So what is happening here? We have a primary particle. The particle interacts at the top of the atmosphere, and then let's suppose this primary particle is a photon. It produces an electron-positron pair here. And then these electrons and positrons will lead to the production of more photons, here in orange, which will, again, produce more of these pairs. We have a cascade process. And this grows exponentially, right? And what we want to do is to try to understand, based on all these particles that we get here at the bottom, we want to understand the properties of the primary particle. How do we do that? Well, first, we need to understand what are the relevant processes going on here. This cascade, the electromagnetic shower, it's an interplay between several processes like Bremsstrahlung, in which we have an electron or a positron interacting with whatever nucleus, leading to the emission of a photon. We also have this other process called Bethe-Heitler pair production, in which a photon, like this, interacts with the air, producing an electron-positron pair. And finally, at some point, we have something that we call ionization losses, and I'm going to explain a bit better, about these ionization losses later. But ionization losses, it's essentially where the cascade stops developing in the atmosphere. But let's just now try to capture a bit of the main properties of an electromagnetic shower. So the key assumptions that go in here is the following. We know that the typical interaction length here, the typical interaction length, lambda interaction, or x0, it's, it's called lambda interaction or x0. We are going to use this information, okay? So the key assumptions is that there is a typical interaction length, x0, that we can use many times. And we are also assuming in this toy model that one particle becomes 2, not 3, not 4, only 2, because that makes our lives much easier. Okay, so let's start doing that. And we also assume that each one, every time 2 particles are generated, like when we have an electron-positron pair, on average, each one takes 50% of the primary energy, which is a very reasonable assumption. So what we are going to do now is, let's start, for example, with an electron or a positron at the beginning, at equals 0, I don't care. So there are n generations of particles in the shower. And, well, after n generations of particles, if the characteristic length it's x0 here, and I'm using these 2 notations, I just want to make it clear, because x0, it's the characteristic length, which is driven by the interaction length, lambda, okay? I don't want to confuse you, so just choose one of them. And then what we have is that the depth after n generations, we have that x is n times x0, which is kind of obvious if you look at the drawing. And what's the typical energy of a particle at the nth generation? So the energy of a particle at the generation n, well, it's the initial energy of the primary particle at the top, divided by 2, because we're generating 2 particles at each interaction, to the power n, which is the number of steps. And the number of particles it's very similar. We have the number of particles, it grows like that, because it splits in 2. Very intuitive. So this cascade will develop in the atmosphere until something happens. What stops the development of the cascade in the atmosphere? Notice that sometimes there is the production of electron-positron pairs. So at some point, your energy is so low that you cannot produce electron-positron pairs, because the energy is below the available energy that would be required to produce like the 2 electrons, right? The rest mass or the rest energy of an electron and a positron. Therefore, at this stage, the cascade can no longer produce an electron-positron pair, and then we have just ionization processes happening. When this happens, I'm going to call this, there is a maximum number of generations, if you assume that. I'm calling this Nmax. And at Nmax, the ionization losses are going to dominate over everything else. And so Nmax again, it's when ionization losses dominate. And when does this happen? It happens when the energy, it's comparable to something that I'm calling EC, which is a critical energy. Once again, critical energy because cannot produce pairs. And therefore, based on that, and on these equations, we can derive very simple relations, and that's what I want to do now. So we know that after n steps, so this is the condition, right? So I'm just going to plug everything in. And that we can get that so that's how we get the maximum number of generations that we can have. And, well, if you look again, on this definition, we want to know what's the value of x for which we have the maximum number of generations. So when does this cascade process starts to be halted and the ionization competing process starts to dominate? Right? So that follows straightforward from here. So we have x0 times n, which implies that right, straightforward, and therefore, from here, what we get is, we just plug this in there. We get something that I'm calling x max. Well, this is a very simple derivation, okay? A very simple toy model. It was done already in the 40s, and although this is very simple, we can do this in like 5 minutes. Well, I imagine that at the time there were many concepts to be learned, so this was more challenging to be done in the 40s. So bottom line, at some point we get to a maximum number of particles in the shower, which corresponds to the ratio of the energies, and we get this thing that I just derived called the X max, right, which depends on this critical energy, which is when the ionization losses start to dominate. Here we have a log base 2, because, well, evidently, this produces 2 particles at every time, so we are going to have 2 to the power of whatever, therefore log base 2, it's the sensible thing to do, and that's how we get X max. Is that clear? Yep. Yep, this is the which ones specifically are you referring to? Mm-hmm. They are important. Yeah, they are important, but in this case, you assume that they are not. Yeah. Yeah, that's the very definition of a toy model. You build a toy model because you want to just get one part of the whole picture. And the part of the whole picture that I'm trying to show here, it's just that there is a point here in which, due to this critical energy, the cascade ceases, yeah. But if you do it right, of course, you have to take into account, yeah. Yeah, yeah, I think you are right. Maybe this is flipped. You might be right, yeah. Yeah, according to the equations, right? You're completely right, yeah. Yes, you were right. Yeah, it's because of, for this reason. Yeah, did everybody hear what Marcelo just said? Yeah, so what he said is completely right. The plot is not correct because This should be flipped, electrons and photons in this plot. Why? Because you produce an electron-positron pair from a photon, not the other way around. That's what he said, so you cannot trust the plot. So you just flip electrons and photons here, essentially, okay? Yeah. Yeah. Okay. Yeah. Yeah, so I should tell the person who did this plot to fix it, yeah. Okay. And now we go to the second part of the model, which is, so far, we talked about the electromagnetic part of the shower only, and then we go for the Heitler-Matthews model for air showers. And the Heitler-Matthews, it's the hadronic generalization of what we just did before. This is a bit more intricate. That's why, well, this was only done in 2005 by Matthews. It describes the development of hadronic showers in the atmosphere. And it's in an interplay of hadronic interactions, pion decays, and all processes involving the electromagnetic showers that we've just seen before. So one very important thing about this model is that 2/3, roughly speaking, correspond to the hadronic part and 1/3 to the electromagnetic part. This is an implicit assumption of the model. And why is that? Well, it's because now, when we have the interactions in the atmosphere, we have the production of a bunch of pions. We have charged pions and we have neutral pions. And what happens? Well, it happens that neutral pions, they decay into photons. Charged pions, they decay into muons plus neutrinos. And then there is, of course, the muon decay. And if you flip the sign of the pion, you flip the signs of everything here. But the principle is the same. Therefore, because you have, statistically speaking, the production of both charge and neutron pions and plus pi zeros, well, it's reasonable to say that this component here, the charge component, it counts 2, and the electromagnetic component counts as 1. At least in this toy model, okay, once again, very, very simplified. And this model only assumes pions. In reality, I just told you that in the history that we have all these other particles being discovered from cosmic ray showers. We have kaons, for example, and other things. So this is very simple just to get an idea of what's going on and the basic dependencies. So the number of pions that we get after n interactions, it's more or less what we want to do something very similar to this now. And how do we do that? Okay, let me continue. So in order to do that, now things are a bit more complicated, and if I get something wrong here, you please tell me. So number of pions, of charged pions after n interactions. That's what we are after. So we can follow a very simple reasoning like we did before. So the number of charged pions after n interactions, it's about 2/3 of what I'm calling n tot. N tot, it's the total number of pions that it's produced at each time. So at each time. So now we have a very similar type of argument. Eventually, what happens is that these particles will interact in the atmosphere. There will be both types of pions, right? Let's just take a look at the charged pions. They will keep developing in the atmosphere. They will produce more pions. That's why it's a cascade. And eventually, the energy will not, like in the other case, will not be sufficient to produce more pions. The energy will be too low. There is, again, a critical energy that will suppress the production of more pions and will allow these pions to decay before they can interact. And now what we need to see here, and okay, let me just write down the typical energy, like we did in the other case. Okay, so the cascade stops when we have, let me call N star, cascade stops at N stars. N star, yeah. Cascade stops. Okay, what's this energy? Well, we can do exactly the same type of thing that we did before. And we can easily show that N star I don't want to do all the calculations here, okay? If you want to try this later on, and if it doesn't work out, you can come to me during the rest of the week. Okay, I'll just show the main results. Then this is divided by... and now we continue doing more or less the same thing that we did before. We want to know, well, when the cascade stops, we also get the decay of the charged pion. So we get to here. Let's forget about the pi zero part. So that we get to the decay of the charged pion. The charged pion will decay and produce a bunch of muons. And when this happens, well, we need to know the number of muons being produced, and mu. The number of muons being produced, it depends, of course, on the number of charged pions at N star, because N star is where this effect starts to kick in. So it's when the cascade halts. And what we get here, therefore, is that the number of muons, and remember that this channel, charged pions, it's 2/3, because we have pi plus, pi minus, pi zero. You can think of it as more or less that it's a 2/3 factor. Where am I? Here, yeah. So there is a critical energy, again, in this case. I'm calling this EC, which is, of course, not the same as before. I'm just using the same notation. E0 to a factor kappa. Let me explain to you how do we get here. Let's look at this expression again. From this expression, we just want to maybe open this up using this energy relation, right? If you just open this up, forget about this line that I wrote. Maybe I was too premature. Just look here. Let's just replace E0 and this is, what did I write here? What's my handwriting? That's, where am I? Yeah, it's EC. Okay, sorry. That didn't make sense. And now, if we just open this up using those energy relations, we get the following. Right? This is important because we are going to use this later. 2/3, again, we are looking only at the charged channel. And total, multiplicity, number of particles produced per interaction. And now we can go back, we can come back to this to estimate the number of muons being produced out of this interaction. So we have number of muons depend, of course, at the number of pions at this stage Here. At this stage, when there is this interaction decay threshold, which depends on the critical energy that I just wrote here. This doesn't. Okay, and now, writing this expression, we can estimate the number of muons. Let me write this just in a slightly more convenient form. Sorry about that, this was messy. So if we have the information of the number of particles produced per interaction, we can exactly calculate what's n star, which is when this process, when the cascade process stops and we start to produce muons. And I can already tell you that the typical number here for air shower cosmic rays in general is something between 5, 10, 15, order 10, okay? And then we can get a factor here that we can use to calculate the number of muons. Okay, now we come back to the number of muons. To something that I'm calling kappa, where kappa is a constant that will come from there. So kappa is an information that you get here if you know how many particles are being produced. Once again, this is something you produce about 10 particles, 10 pions, and therefore this kappa factor that you're going to get in the end is going to be something like the order of 0.8, 0.9, something like that. Maybe 0.95, I guess. It all depends on the energy and on the number of particles being produced. So with that, we have another observable. First observable that we got was from electromagnetic showers. We got the Xmax, and we also got the Nmax, so the maximum number of particles. Now we know how many muons are being produced in our shower, and that's a lot of information to characterize the shower itself. Yep? It completely dominates over the ionization length, except close to the threshold. Close to the threshold, you have some effects kicking in because they are comparable. But for most of the generations here at the top, it completely dominates such that you can ignore the other. I mean, when you build a model, you don't. When you're building an observatory and reconstructing, you don't ignore it. But for the model, you do. Yeah? Okay, so now what I want to do, just to finish this part of the air showers, because I don't want to extend myself too much, is just to write down Xmax like we did before, because this is a very important quantity. This quantity is telling us where in the atmosphere, in the development of the shower, if you just look at it vertically, where, at which height, x, more or less, the shower reaches its maximum, or the maximum number of particles, or, you know, because this is a very important observable to infer properties of the shower, like energy, like composition, and so on. And now I'm going to move a bit faster on this part. So Xmax, in this case, for the Heitler-Matthews model, would depend on the typical interaction length here, right, that people call usually something like X1. It's the first interaction. And then we have something very similar to what we had before. This is the first interaction. X0, the same as before. Here, we have this x1, which is slightly different because x1, it has something to do with the pi zero part. And now I'll stop and go a bit slower. Why? Because so far, this, we did the muon part, we are talking about the hadronic part only. But if we are considering the pi zero side of things, this leads to an electromagnetic shower, which is just the one that we did before. Same thing, same thing. And well, we have a nucleus, it produces a bunch of pions. And if we have a pi zero being produced, the pi zero will decay very fast. The typical lifetime of the pi zero in its rest frame, it's like, I think, 10 to the minus 17 seconds. Whereas the lifetime of the charged pion in its own rest frame, it's of the order of maybe 10 to the minus, I forgot the number, minus 8. Okay, yeah, good, thank you. So 10 to the minus 8 seconds. But it's much larger than the pi zero. So the pi zero, here, well, it decays very fast. It leads to electromagnetic showers. And therefore, the electromagnetic shower, it grows. One particle produces 2, produces 4, and so on. So it tends to dominate the total number of particles in the cascade in general. Even though it's 2/3 here and 1/3 here, the electromagnetic part, it grows very fast, and it comes from here. So if we are trying to count, just count the absolute number of particles being produced in a shower, we have to consider everything. And this side will likely be important. How important? Well, very important, actually. It completely dominates. So what we need to understand here is essentially that we have this pi zero decaying and producing another shower. That's why we have this x0 coming back again. The x0 here, it has to do with the typical interaction length, the same one that we had before for the electromagnetic shower, right? Because what I'm writing here, it's essentially the length of interaction, the interaction length here of one generation. And then there is this part, the x0, which comes from the electromagnetic shower. It's a very similar type of reasoning from before. Yeah, I think I already wrote it. So this is the first interaction, just to make it clear. And yeah, the first interaction, once again, it produces the electromagnetic component of the shower. Everything here, same reason as the other one. And I didn't write down this part, but I'd like to just tell you how things change when you have a nucleus, because this is usually what you do when you don't have a nucleus. But if you really want to complicate the model, well, it can be a nucleus. Even though I wrote a nucleus here, what I was doing is just assuming any type of hadron. There is an A dependence here. A is the mass of the nucleus. So we can have like a nucleus with an atomic number Z and a total mass A and a total number of neutrons, of course, A minus Z. So there will be an A dependence here. So to the 0th order, like the very simple thing that you can do is imagine that a nucleus, it's not a nucleus, it's a bunch of nucleons. It's A nucleons. And then you just do everything here for A nucleons. Okay? That's the generalization. And the bottom line here is that once we get this X max for the hadronic part, it's important to understand that X max, it's proportional to the log of the initial energy. It's a very important result. The maximum number of particles, it's proportional to E0, to the initial energy for the electromagnetic shower, for the electromagnetic part, and to E0 to that kappa factor for the hadronic part. Yeah, these are the main features. The toy model is capturing this type of behavior, and that's why I was developing it right now, because it's instructive. And why am I telling you all of this? It's because all of this information is what we need to understand everything with cosmic rays, right? I'm going to talk most of the course about like except for this first lecture, about the theory part, sources, acceleration, propagation, but this is important. This is the connection between what we detect here and what's out there. You need to be able to reconstruct. You need to be able, especially, you need to know that we are estimating number of muons, and the number of muons, it goes like this with the energy to a given factor here, which is just a bit less than 1, and so on. Okay, this is what we usually get from an air shower experiment. This is a toy model. We refine things. We use simulations. That's what we do in a real experiment to reconstruct. But this gives you the general features. And the general features, they do hold. This, for example, the dependence on, logarithmic dependence on the energy of the primary. This holds, okay? Even if you include, for example, you asked about the relativistic effects. If you include relativistic effects, if you start to consider, you asked about ionization. If you consider everything else there, of course they are important. This changes a bit, the numbers change, they have to be adjusted, but this is pretty good. This gives you an idea of how things go. So intuitively, if you were starting in your career to do cosmic rays, I would say this is an important result. You need to know that it goes with the log of the primary energy and so on. Okay? Now, let me move here again. So I wrote these results before here at the board. Main results are these. I think the X-max, once again, this is an observable that is going to come back all the time. And now let's take a closer look at what actually happens. So let's suppose we have a photon at the top of the atmosphere. The photon has an energy of 100 GeV, or 10 TeV, or 1 PeV. If you are looking, so what I'm calling XY and XZ here, Z is the vertical, XY it's our plane here. So this is the Earth plane, or if you're just looking up and the shower is hitting you, that's what you see here. Or if you are just looking from far away from the side of the Earth, from a satellite, this is what you see, the profile. Okay? What are we seeing here? Well, it's very obvious, right? As we increase the energy, the number of particles being produced, it increases. This is very obvious, but it follows from everything that we just did. Exactly? No, but to a good approximation. This is what happens for the photons. What if we had a proton air shower? Let's take a look at the left first. Once again, the XY plane is just looking up, and this is just looking at the development of the shower. For low-energy protons, if the proton is insiding at the atmosphere with a zenith angle theta equals 0, so a vertical proton, this is what we get. You know, it's actually not even that symmetric. There are not that many events. As we increase the energy for the vertical ones, look, we have way more particles. Now we also have these green particles. This is not the screen this time. We have also these green particles because we are producing a bunch of other particles, not only electrons and photons. We have muons, we have other things, and so on. And now, these are for vertical protons coming exactly from here, zenith angle equals 0. What happens if we tilt it? If we look at a 45-degree angle, let's fix the energy at 1 PeV. Well, if it's a 45-degree angle, this is what's going to happen. Now I'm just taking a look at the side profile, right? We have this development, and at a 60-degree angle, we have this other profile. Important features here, it's the depth at which this red blob, it starts to appear. Visually speaking, you know, it's not a scientific term, red blob, but you can see that it's a bit deeper. You know, it depends a bit on the energy, the angle, and so on. You can take a look at the depth. This is telling you something about the shower. So if you do this a lot, nowadays you can, of course, train an AI to do that for you, but if you do this a lot and look at enough showers, you get this feeling at some point. And now, let's take a look, instead of a proton shower, at an iron shower. An iron shower at 100 GeV, vertical. Almost nothing happens. You can barely see that. At 10 TeV, well, that's quite a lot of particles, a lot is happening here, and at 100, at 1 PeV, you can, it occupies the whole box here. It's really a lot of particles. And now let's take a look at the three of them together, developing in the atmosphere. These are actually simulations, okay? These are no longer toy models. We have an array detectors in these blue cyan dots at ground level. This is what's happening. If we have a gamma ray with a given energy, which I cannot read, well, I still cannot read. I think it's 10 to the 15, all of them. Yes, it's 15. So they all have 10 to the 15 electron volts. See, the gamma ray. The gamma ray, it's very penetrating. It goes in, it starts interacting down here. Look at the protons and look at the iron. What's remarkable about these two, well, these two are directly comparable, it's that this produces really a lot of particles, way more particles than this one, for a single interaction. Which is kind of expected, because I said that the superposition idea that we just consider, like, roughly speaking, a nucleus as, for example, an iron, it's a bunch of nucleons, so you just multiply, that's expected. So you do expect to have way more particles for a nucleus than for the simple hydrogen or proton case. And these are the detectors. So we are learning something from this. We are learning that if we have detectors, this is distance in meters. If we have detectors, we can sample a few of these particles and try to do the reconstruction process that I've been talking about. And this brings me back to this plot that I've shown you before. So the particle, the cosmic ray, was entering here, and then we can just draw an X, and we can count the number of particles as a function of the depth in the atmosphere. And there is, if you draw this curve, remember, there is always a point at which the cascade development halts. It stops, right? When you have, in the case of the electromagnetic shower, it was the ionization, losses, and so on. So the particles, there is a bunch of particles being produced. At some point, there is not enough energy to produce more particles. Then other processes start to kick in. And this is where we get this X-max. This profile, this X-max profile, is what actually fluorescence telescopes, for example, try to infer from the measurements. Because there are relations that connect X-max to the fluorescence light emitted. So yeah, this is pretty much what cosmic ray experiments are doing deep down. And why am I always talking about this X-max? Yep. What did you say at the end? For the electromagnetic one? Yeah. Well, there is, if you just come back to this one, no, not this one. Yeah, it has to do, there are several factors at play here, but the main one, it's the atmosphere absorption, right? You're just traversing more matter. But you were interested in the muon part, in the end for the... A proton shower, like a nucleus. Ah, okay, a nuclear shower, yeah. Yeah, okay, that we have to go back. It's what? Yeah, you just, ultimately, I'm looking for the plot here again. So ultimately, you have more muons compared to everything else, but it doesn't mean that you have more, that's what Ulysses just said, more absolute number of muons from this plot. Because what I was going to tell you is that start tilting this plot, this shower. It will traverse more matter in the atmosphere, and you are going to have more generations, and if you slice your generations diagonally, now, because, well, that's how you have to do it, the muons, they, part of the particles, they will keep going forward. I'm not going to point this at my eye, so I'll point the other side. The particles will keep coming here, and you are going to be producing still some muons here. So you're going to have more muons, sure. And the other particles, they might not reach your detector. They might just, keep going. So I think this statement, it has to do with relative quantities, not absolute values. So I'm always talking about this Xmax, and I plan to stop very soon, actually. Why am I talking about this Xmax? Because, well, let's take a look at an iron profile, Xmax profile. So there is the amount of energy deposited in the atmosphere, and there is this thing called slant depth, which has units of mass per area. So it's just mass per area. You can imagine what that means. And you have protons. So the iron showers, of course I drew this by hand, but the iron showers, they are very close if you draw like their profile, the amount of energy deposited as a function of this quantity, that's the slant depth. Why? Because you have more particles. So higher statistics, less variance. It's easy to understand why. Here you have protons, so the showers, they fluctuate quite a lot. So the point at which you have this maximum, which kind of relates to the Xmax, it changes a bit. But for iron, it's kind of more fixed, so it varies less. Therefore, we are extracting another piece of important information. Heavier composition tends to have a lower variance in terms of Xmax, whereas a lighter composition tends to have a higher variance, right? And then you have photons, which has a higher variance for obvious reasons. And then the task is, if you just take one of these curves, how do you know which one that is? Well, actually, there is no way of knowing which one it is in principle. Nowadays, what people have been trying to do is to compare that. They have been training neural networks with tons of simulations to try to be able to tell, okay, this shower that I'm seeing, it's a proton or it's an iron. I mean, usually it's easy to separate photon from the others, because here you have muons, here you don't. This is very simple. So if you have two types of detection techniques, not only one, if you have, for example, water Cherenkov tanks, then you have muons, right? Then it's easier to separate the electromagnetic part, like the photons. That's why some experiments, like Auger, for example, the telescope array as well, they employ multiple techniques. Because look here, it's hard to, you cannot, in principle, separate. And now, at least by using two techniques like fluorescence and these water Cherenkov detectors, you can separate the orange one, the photons. But you still have the problem of how to separate these two things. That's, we don't really know how to separate it very well. Okay, since I'm very, very late, actually, yeah, I'm extremely late. So, yeah, the cool thing about this type of techniques that I'm mentioning, I'm going to go fast, sorry. The cool thing about this type of techniques, this air shower thing, is that this is common to all air shower experiments. Whatever primary particle you have that produces a shower in the atmosphere, this is the strategy that you use. This toy model can be applied. This type of intuitive information that we should try to build, it can be applied. So it's one experiment that allows you to do many things. You can do like particle, you can study astrophysics, gamma rays, particle acceleration. You can do like neutrinos, photons, like the full multi-messenger astrophysics, the full thing. But you can also do like solar physics sometimes with this type of experience, because if you have a telescope looking for light in our own atmosphere in a dark night, well, maybe there is something going on there emitting light, something that it's not a cosmic particle, but it's still interesting science that can be done. You can do many things like fundamental physics and particle physics, especially this particle physics. I think it's rather obvious that the particle physics part of Astroparticle, it's very strong here in cosmic rays. Okay, there are many experiments nowadays. I'm sorry if I forgot. I didn't forget. Actually, I just omitted them deliberately. I just wanted to mention a few that I know are no longer operating, but that are relevant for the science case that we are discussing. Cascade Grande, for example, it's this one is in Germany. It's no longer operating. It stopped, I think, in 2010, 11, maybe. Yeah, this was an experiment dedicated to the energy, to studying cosmic rays in the energy between 10 to the 15 and 10 to the 17 electron volts, more or less. Okay, like the transition between what's galactic and what's extragalactic. That's Cascade Grande. There was, early on, like maybe 20, 30 years ago, HIRES, the high-resolution fly's-eye experiment. This was a fluorescence detector. These are water Cherenkov tanks. So there was this fly's eye. This was very important early on in the history of especially ultra-high energy cosmic rays. It was observing particles above 10 to the 18 electron volts or so. Nowadays, we have things like LASSO. Many of you know LASSO for the gamma ray part, but they also do cosmic rays because, once again, same technique, same thing. There is no way to separate it. I mean, of course, there is a way to separate it, but it's the same experiment, I mean. So you can see many, or you probably can't because I can't, but you see some structure here, right? Around these structures here, there are detectors, and here there is also this part, which is, this is a picture of what's inside here. So they have two types of detectors depending on what they are trying to do. And at high energies, ultra high energies especially, we have the telescope array in the US and the Pierre Roger Observatory in Argentina, which many people here in Brazil as well and South America work on. So we have this telescope array. Originally, they came from this logo. It's because they did a lot of fluorescence observations. We have Auger as well, in which you have like many techniques, including orange Cherenkov, fluorescence, and so on. So here are fluorescence telescopes, like this Loma Amarilla, Los Morados, Coihueco, and so on, around here. And each one of these dots here, it's one of these orange Cherenkov tanks. They are named. Some of them have cute names, so if you got the chance to deploy one of them in the field when it was being built, you could have named your own tank. So you can also see like their solar panel for energy and so on. And here, where is that? Here, Malargüe, it's where the site of the Pierre Roger Observatory is, the central. That's where this is when I was doing my master's. I did in Auger, and we have to spend the night there looking at the screens. Well, it's pretty much looking at the screen because there isn't, usually nothing goes wrong, which is good. So the last thing that I had for today is, or the last few things that I have, I promise I'm finishing. Yeah, I still have time. Okay. So once again, these animations are very similar to the ones that we saw before. We have X, Y here. So just looking at the shower vertically. And we have the profile here. The horizontal axis, it's the number of particles, essentially. Here, also number of particles as a function of the radius. So just combine X and Y. This is for, what's the difference? What's the difference? Oh, yeah, here it's the Z-axis. That's what changed. This is ZR. OK, yeah. It just depends how you are looking, but this is the same shower, probably. So you see in physical units how this spreads. So this is for a 10 to the 14 electron volt shower. I'm not even talking about the highest energies yet. I'm not talking about 10 to the 20. I'm talking about 10 to the 14. And we already have a shower covering like 1 kilometer. That tells you something. That's telling you how big your detector should be. Also, here vertically, we have like 20 kilometers and so on. So that tells you how far away you should put your fluorescence telescopes from the point where you'd like to observe. So you have to combine these two things, these two types of information, when you are thinking about how to build an observatory. And now, I think this is one of the last parts that I had for today. So for a discussion, you know, we all have a scientific goal. If you're studying cosmic rays or whatever particle you're doing, you want to do some science in the end, right? Even if you're doing like this reconstruction part and so on, you want to do the science in the end. There is a science goal. So suppose I gave you money, a lot of money, but just with the condition to build a cosmic ray or an air shower type of experiment. So, you know, just as a discussion, free discussion, we have like 5 minutes before the coffee break, right? So what would you do with that depending on your science? So what? SWGO. So Ulysses already has his answer. He's already doing it, SWGO. So, but the things that you have to take into account are this. Well, yeah, show me the money. I don't have the money. If I had it, I would have done it already. Or maybe not. I would probably keep the money. No, just kidding. But yeah, for discussion, things to think about. Energy, angular resolution, so how well we can point to one direction. Like the composition is essentially that X max. We measure X max, and with that we infer the composition. The location of the experiment. So just brainstorming session. Considering these things, if we have a science goal, let's suppose we have the science goal of detecting ultra-high energy cosmic rays, the highest energies. What should we think of now that we learned about air showers? How should we design in terms of area, sizes, and so on, spacing, grid spacing? How should we design our detector to achieve these goals? What should we think of? There is no right answer. Density of detector. So what does the density of detector tells us? Exactly. So very good. So she just said that we should think about the density of the detectors. There are two things, very, very broadly speaking. Well, if we are aiming for the highest energies, your shower is very big. It occupies a very large area, right? 10 to the 20 electron volts and so on. So you should think of which science you are doing first, if you're going for the highest energies. So the maximum, if you're at the highest energy part, so the total area covered, it has something to do with the maximum energy. And what she just said, the minimum energy, so the spacing tells us the lower energy threshold. So in principle, we could think of it as, if we had something, let me call this efficiency of detection, we have here energy, we have a minimum energy, we have a maximum energy, so we fix this from the beginning if we want to build an experiment, right? The maximum energy here, well, we need, this is driven by the area. So we know how big of an area we should instrument based on the maximum energy. And we know, if we know how low in energy we want to go, that's how we decide the spacing. Like if we have a grid of detectors, the spacing is driven by the minimum energy, right? Of course, things are not that simple. It's never a function like this, optimal 100% everywhere, right? There is always something that you want to do, something that you have to sacrifice, like, usually you end up with something like this. Maybe it's not symmetric, but so on. You always lose efficiency in one of the edges and so on. That's why no experiment is fully efficient at far away from what they were designed to do. Second thing, angular resolution. You want to be able to point to a direction. And I have 1 minute, and so let's finish this. Angular resolution. So we need to think about, like, if you're doing reconstruction, regular arrays are, of course, easier to reconstruct things instead of a very weird type of array, although nowadays this is not a problem with all the computational resources. Composition sensitivity. We need to be able to separate muons, electrons, because, well, this is the hadronic part of the shower and the other part of the shower, the electromagnetic part of the shower. If we use both techniques, we can do better particle discrimination. We can remove all the photons from our sample, and we can just keep the cosmic rays that we're interested in. We also have to think about the X-max resolution. So we need to be able to tell where the shower reached the maximum within a reasonable value, delta X, around X-max. Because the value at which the shower reaches the maximum, as we're going to see later, it's a direct proxy for the composition. It tells us whether it's a proton, whether it's a nitrogen, or iron nucleus, the cosmic ray. And the location. So, for example, Ulysses just mentioned that if I gave him money, he would build a high-altitude detector. He's already doing that, SWGO, right? I don't know, it's 3,000, what's the altitude? 5,000, whoa, that's a lot. Okay, so they are building a very high-altitude one. Why? Because if you build it at high altitude, the atmosphere stays the same. So you're just intercepting the shower development early on. So these are the things that you should consider, right? If you're doing like the other techniques like radio detection, well, you want to be radio quiet. You don't want people talking in walkie-talks close to your experiment. If you have fluorescence detectors, you don't want to put it in the middle of the Amazon forest, because for obvious reason, it's going to rain at 5 p.m. and you know, it's going to be difficult to do measurements. So yeah, that's the things that we consider, and that's how we link all of this. We decide the science. We have this type of toy model. Of course, this is toy just for understanding. We can improve it. We actually do use improved models. And we think of the science you want to do, and we consider all these things. This list is evidently not complete. I'll stop here. Yeah.
It was a long applause. Questions?
Hi, thank you. I have a question more out of curiosity. How did they reconstruct a 10 to 20 EV event in 62?
Same way they do today. But it was just a surface detector. So actually, yeah, so the hadronic interaction models were not good at the time. They had a very simple intuition of what to do. There is a lot of uncertainty, so there are sources that actually think it's not 10 to the 20. Some people say it's less. But statistically speaking, there is no reason for it not to be 10 to the 20 electron volts. But the techniques employed, it's the same one as you would employ today, more or less, using a surface-only type of detector, a water Cherenkov detectors. You would count the voltage, like vertical, like the muons going there, and so on. You would convert that into a signal. You see the distance and the timing. The timing information was very good. Well, not very good, but you need that information to actually get the direction and so on. So to my knowledge, I didn't check the original paper, but it's very similar to what it's done today. With much worse models and without computers, which make it way more impressive.
Yes. Okay, can you go back to the slide where you showed how the iron shower develops, the one with the angular, yeah. Because it looks...
this one.
No, go forward. More.
Ah.
The one with the red blobs.
Okay. Yeah, the Korsakoff simulation. These ones, yeah, got it.
You said that I can think of iron as a bunch of nucleons, but why does it fail for lower energies? Or is it the angle? Because the first one looks very different from a proton shower with the same energy.
Thresholds. So because it scales with energy over number of nucleons. So if you want to do the comparison between the two cases, you would need to compare an iron with a proton shower, an iron shower with a proton shower, 56 times lower in energy. Because so it goes with E over A.
Okay, I see.
Yeah. Very roughly speaking, it's not exactly. Yeah.
Other?
Okay, I would like to ask something from like the perspective of building a water Cherenkov detector.
Mm-hmm.
So, like, what is there a threshold of the amount of particles that I capture beyond which I can't reconstruct the event? Like, say, if I only capture 20% of the shower, can I reconstruct, or is there a threshold like that?
Yes, there is a threshold. You need to have a decent sample of particles to reconstruct. I have no idea about the numbers, okay. But there is a threshold because ultimately you have to remove your background. So sometimes things just happen. Your detector detects things that are not there. You have this type of systematics.
Yeah, because if the angles are different, I might get only some parts of the shower, right?
Yeah.
Within the area of my detector array.
Yeah, but
so,
I have no idea about the numbers, though.
Okay.
Yeah.
And also, like, Xmax is the distance where the cascade is stopping.
It's where the shower reaches its maximum in the atmosphere. So if you count here, just imagine that you are counting in horizontal slices. Here, you see that you have a lot of particles.
Yes.
And here, it's decreasing. This profile, this is Xmax.
Okay.
It's where the shower reaches its maximum number of particles.
Okay, so if I'm building a detector, do I want to build it at Xmax or lower or much lower? Like,
That depends on your science goal, ultimately. It's one of the questions of this discussion that we had in the end. It depends on what you are trying to do. Sometimes it's advantageous if you're closer to Xmax because it's fewer layers to reconstruct.
Yeah, okay.
Yeah, but sometimes it's not because you want more particles spread over a larger area.
Okay. Thank you.
Claudio,
Can I?
he's also building SWG also.
Important information. So if you only have ground detectors and not the fluorescence, you cannot tell if you are, I mean, where Xmax is, right?
You cannot.
Right, yes.
Yeah. Oh,
Because you don't know
Yeah.
when the shower started, actually.
yeah.
So,
I mean,
so it gives you an uncertainty in the energy.
Yeah, there is a way, in principle, if you know the model, statistically speaking, if you have many showers, it's possible to guess. Yeah.
In average, not
Yeah.
per individual shower.
Yeah.
I have a similar question to yours. If we have only water Cherenkov detectors, how can we calibrate the energy? Because in the Pierre Rouget Observatory, normally use the fluorescence detectors to calibrate the energies. So how can we do it without a fluorescence detector?
That's a problem. Yeah, I don't know how to calibrate without fluorescence at these energies, right? Because, well, but for depending on the energy range, you can use other ways of calibrating things that you know. You know, it all depends. Sometimes, like, you can use external sources. You can just inject a signal. People did that in the past, I think. But I don't know in practice how people do that. I'm not that much into the building part.
You mean for individual detectors or for the estimation of the energy of the shower as a whole? That's done from, I imagine, simulations, inference from the energy deposit. You simulate what the expected energy deposited at the ground, and from that you will infer with a large error what would be.
But I think he's also asking, I don't know if that's what you are asking, but how in the 60s, how was that volcano range event done in that case? How would you calibrate that water Cherenkov detector?
Yeah, because in the Rouget Observatory, we use the fluorescence detector to calibrate the surface arrays. So without a fluorescence detector, how could we do it in the back?
Well, as far as I understand, you have to compare with simulations.
Yeah, Marcelo knows probably.
Volcano range was scintillator detectors. And Havara Park, which was the first Cherenkov detectors, both were done through calibrations. So you're absolutely right. There's no way to, through simulations. There's no other way to infer the energy if you don't do the simulations. But in case of the volcano range, it was scintillators.
Anyone else?
There is one here.
So
There's one here, Ulysses. Can I can pass it to her.
Okay, thank you for the good talk. I was going to ask, you mentioned that we care about directionality when studying cosmic rays, but why do we care? Because they get deflected by everything in the universe. So for me, that I study gamma rays, cosmic rays are noise. So I really do care, sorry.
Yeah. You can ask, let's come back to this in detail later. Let me just give the short answer. The short answer is, it depends on the energy. If you're up to, like recently there was the second most energetic cosmic ray event ever. Like I think it was maybe 400 EV, so 4 times 10 to the 20 electron volts. There is a lot of magnetic field uncertainty. We know that, I'm going to talk about that on Thursday, tomorrow. So in principle, if you know the magnetic field well enough, which you don't, actually, we really don't know the magnetic field, it would be good to point to 0.1 degree instead of 1 degree, because the sky is 4 pi. right? Imagine that you put like dots, pixels of 1 degree in the sky. That's a lot of sources. So the better angular resolution, if you go to these high energies, the better. So the best angular resolution possible. Only to the, for the high energies. For the low energies, yeah.
Okay.
But ask me again about when I talk about magnetic fields tomorrow.
Coffee?
Coffee?
Yes, good.
Yeah, I'll save time later.